Inside the heart of a mega factory, a river of molten glass flows like liquid fire. At nearly 1,700 degrees Celsius, the air vibrates with heat so intense it can melt steel. Flames pulse beneath the furnace as bright orange waves roll forward, shaping the future of everything from skyscraper windows to your phone screen. Sparks rise like tiny shooting stars caught in the roar of industrial power. It's violent, mesmerizing, and almost impossible to believe that this blazing chaos will soon become something perfectly clear. This is where the story of glass ends, and where our journey backward begins. In just a few hours, this molten river of fire will transform into some of the most essential materials of modern life. It will cool into flawless sheets that reach the heights of skyscrapers, shield families inside their homes, and form the giant facades of airports and stadiums. It will stretch into crystal-clear windshields built to withstand storms, debris, and high-speed travel. It will become laboratory glass, strong enough to hold corrosive chemicals, and delicate enough to measure a single drop. It will even turn into the screens you tap every day. Thin, durable, and perfectly smooth. Every year, mega factories like this produce millions of tons of glass, feeding construction, medicine, transportation, and technology. The world literally shines because of what happens inside places like this. But these impressive final forms hide an even more incredible truth. Glass begins as a material so basic that most people never give it a second thought. To truly understand this transformation, we won't follow the process forward. Instead, we'll rewind it, layer by layer, stage by stage, until we return to its simplest, most surprising origin. So let's reverse the journey. Let's unmake the modern world's clearest material, tracing it backward from perfection to purity, from finished strength to fragile beginnings. Only then can we see how something ordinary becomes extraordinary. We begin our backward journey at the point where glass earns its final approval. Before any sheet is allowed to leave the factory, it must survive one of the most demanding quality control systems in modern manufacturing. Rows of high-precision laser scanners sweep across the surface, reading every square inch with microscopic accuracy. These beams detect imperfections far too small for the human eye: air bubbles, microcracks, or tiny particles trapped deep inside the structure. Even a flaw smaller than a grain of dust can weaken the glass, causing problems months or years later. As we reverse the process, we watch rejected sheets roll backward along the conveyor, returning to the moment just before their flaw was discovered. A bottle traced in reverse flows out of its shape and melts back into a glowing droplet. A massive window panel retreats from the cutting table, lifting back into the furnace where its edges soften once more. The perfect sheets, those that passed every test, move backward into the long annealing chamber. This is where the glass regains its heat, rising slowly from room temperature to a glowing red that signals it's nearing its molten state again. But in forward time, this step is critical. The annealing process prevents the glass from holding internal stress. Without it, the slightest temperature change or sudden pressure could cause catastrophic failure. This long, controlled reheating and cooling cycle ensures that skyscraper windows don't suddenly shatter, that windshields remain stable, and that countless products stay strong for decades. Rewinding further, we watch robotic arms unbreak cracked pieces, restoring them to seamless form as the temperature rises. Bubbles disappear as molten flow smooths them out, like rewinding the formation of flaws back into pure liquid. It's a reminder that clarity is not accidental. It's engineered with precision and perfected through intense scrutiny. By stepping backward through this stage, we see the extraordinary standards needed to produce something so simple looking. A single imperfection can shape an entire product's life. And now, as we continue in reverse, we move deeper into the heat where shape itself begins. Leaving the inspection stage behind, our reverse journey takes us deeper into the factory, where finished glass begins to soften again as we roll backward into the annealing layer. In real time, this enormous tunnel is where glass cools slowly and carefully. But as we rewind the process, temperature rises instead of falling. Sheets regain a subtle glow, then a bright orange warmth, and soon they soften into a flexible state. Not yet liquid, but no longer rigid. Stress patterns that were once carefully removed reappear, as if time itself is restoring tension to the material. Moving further back, we return to the shaping zone, where precision and creativity meet industrial power. In forward motion, this is where molten glass is formed into everything from architectural panels to everyday bottles. But now, as we reverse the footage, bottles unblow themselves. Their necks shrink inward, their bodies collapse smoothly, and they fall back into glowing droplets of liquid. Windshields lift from cutting robots and drift backward toward the molds that originally gave them shape. Each form loses its structure as it warms, returning to a flowing state. For float glass, used in skyscrapers, the reverse transformation is especially mesmerizing. Giant ribbons of glass slide backwards from perfectly flat sheets into thick, uneven layers that seem to ripple like water. They retreat across the factory floor toward a massive pool of molten tin. Normally, molten glass is poured onto the tin so it can float and spread into a flawlessly smooth surface. But in reverse, the sheet appears to rise upward from the tin's mirror-like surface, folding into itself as it retracts toward the furnace. The shaping of glass is a dance between heat, gravity, and machinery. In normal time, powerful blowers, rollers, and molds work in harmony to give every product its exact form. But reverse, the process feels like watching objects surrender their identities. Bottles lose their volume, jars lose their edges, panels lose their precision. All of them become shapes melting back into the glowing stream from which they came. This step reveals a simple truth. Glass is only hard and permanent when cooled. At high heat, it behaves more like honey, thick, viscous, and constantly moving. To understand how factories control this fluid with such precision, we must continue back toward the source of all heat and transformation. And so, our journey moves closer to the heart of the operation, the massive furnace that fuels the entire industry. As we continue reversing time, we move from the shaping floor toward the core of the factory, the massive melting furnace. In forward time, this is where raw materials are transformed into molten glass. But now, traveling backward, we watch the brightly glowing stream retreat into the roaring chamber that birthed it. The heat intensifies with every step, changing from a warm orange to a blinding white at the center. Here, temperatures soar to nearly 1,700 degrees Celsius, enough to dissolve minerals that would otherwise remain solid forever. In reverse, the molten river begins to climb back into the furnace mouth, defying gravity. Droplets leap upward, merging into larger flows as the liquid climbs the glowing walls. Sparks seem to fly backward into the burners, swallowed by the flames that originally produced them. It's like watching a volcano pull its lava back into the earth. The effect is surreal, but it reminds us that glass exists only because of unimaginable heat and relentless energy. At full operation, furnaces like this run continuously for years, sometimes a decade or more, without ever cooling down. They are engineered to operate non-stop, feeding an unbroken stream of molten material to the shaping floor. The raw ingredients melt under cyclones of heat: silica sand, soda ash, limestone, and recycled glass. In forward time, these ingredients blend and liquefy until they lose all memory of their solid form. But in reverse, we see tiny particles reforming in the fiery glow, reassembling into powders and grains. The deeper we rewind, the more chaotic the furnace appears. Instead of melting everything into a smooth, even flow, the material breaks apart into individual components. The once unified molten pool separates into glowing fragments. You can almost identify the different minerals as they regain color and texture. Soda ash reforms into pale crystals. Limestone gathers in powdery clusters. Recycled glass, known as cullet, solidifies first, appearing like sharp, translucent shards that rise out of the heat. This reverse transformation shows us how much precision is required to melt such a stubborn mixture. Silica, the main ingredient, has one of the highest melting points of any common mineral. Without soda ash and cullet, melting sand alone would demand even more energy. This is why factories carefully engineer the recipe long before materials ever reach the furnace. Watching the molten glass reassemble into raw components reveals something else. Glass isn't a traditional liquid or solid. It's a unique state of matter called an amorphous solid. Its molecules freeze into a disordered arrangement, almost like a liquid trapped in time. And to unlock that structure, the furnace must push the material past the limits of normal transformation. Now that we've traced the molten glass backward into its elemental form, there's only one place left to go: the mixing stage, where the ingredients first come together before facing the heat of the furnace. Rewinding further, we leave the blinding heat of the furnace and step into the batching zone, the brain of the operation. In forward time, this is where precise measurements of raw materials are combined to create the perfect glass formula. But now, moving backward, we watch the unified mixture unravel into its individual parts. Streams of powder separate in midair, reversing their fall into giant steel hoppers above. Each material rises like dust caught in a reversed storm, drifting back toward the silos that once held them. In real time, every batch begins with silica sand, making up nearly 70% of most glass. It's the ingredient responsible for clarity, structure, and strength. In reverse, grains of silica extract themselves from the blend, returning to a shimmering white pile that looks almost like powdered snow. Beside it, the soda ash pulls away, forming its own pale gray mound. Normally, this material lowers the melting point of silica, making it possible to liquefy sand without unimaginable energy. But here, reversing the flow, it regains its granular identity. Next, limestone lifts from the mixture, clustering into soft, chalk-like particles. In forward motion, it prevents glass from dissolving in water or breaking down over time. But traveling backward, we see it separate effortlessly, as if the ingredients know exactly where they came from. Finally, cullet, crushed recycled glass, rises from the batch in sparkling fragments. Colored pieces, clear shards, and tiny glints of reflected light swirl upward and return to their storage bins. In real production, cullet is essential for lowering energy use. It melts faster than raw minerals and allows factories to save both fuel and time. This reverse deconstruction reveals just how much engineering goes into a single batch of glass. Each component must be measured to the exact gram, ensuring the final product has the right strength, clarity, and durability. Automated systems control the flow with incredible accuracy. Load cells weigh each ingredient. Gates open and close with perfect timing. Conveyor belts deliver the blend without interruptions. And mixers churn the materials together until they're completely uniform. But backward motion changes everything. Mixers appear to unturn, folding the mixture outward instead of blending it in. Powders lift from the blades in spiraling clouds. Conveyor belts run in reverse, carrying the materials away from the furnace instead of toward it. Hoppers close just before they would have opened, sealing the silos once more. By witnessing the ingredients separate, we get a rare look at the complexity hidden behind something so simple. Every window, every bottle, every fiber of glass begins long before the furnace, with a precise formula designed to withstand stress, heat, impact, and time. And now, with the recipe undone, we can finally move further back to where these materials begin. The purification process that turns raw sand into the pure silica needed for perfect glass. As we continue reversing the journey, we step into the purification zone, one of the most overlooked yet essential stages of glass production. In forward time, this is where raw sand is cleaned, refined, and transformed into high-quality silica. But now, moving backward, the immaculate white grains begin to darken. They gather traces of minerals, clay, and organic debris as if the purity is slowly being peeled away, layer by layer. In real operation, sand enters massive washing drums, where high-pressure water jets blast away unwanted contaminants. But in reverse, water flows upward, climbing against gravity, pulling dirt and silt back into the sand instead of removing it. Filtration screens unclog themselves as particles jump backward from their steel surfaces. Mud and clay swirl into the mix, giving the once clean grains a faint yellow tone. What was pure becomes imperfect again. Magnetic separators, which normally remove iron particles, now work in reverse. Tiny flecks of metal lift from collection trays and scatter into the flowing sand. These iron impurities are critical to observe, because even the smallest amount can tint finished glass green. Watching them rejoin the material reminds us how delicate the balance of perfection truly is. One stray mineral can alter an entire production run. Further along the reversed conveyor, hot air drying towers begin to inhale rather than exhale. The warm atmosphere pulls moisture back into the sand, dampening the grains as if the desert air is returning. Fans spin backward, their blades sucking humidity into the column instead of pushing it out. Clumps form in the once smooth stream, making the sand heavier, darker, and rawer with every passing second. Chemical purification also unwinds itself. In forward motion, special agents help separate organics and carbon residues. But now, those contaminants reappear, drifting back toward the sand like ash settling after a fire. Each impurity returns to its original place, giving the material the rugged, natural texture it had before processing began. Eventually, as our journey rewinds further, we witness the sand lose nearly all its refined character. Gone is the bright silica. Gone is the uniformity. What remains is a wild mixture. Irregular grains, flecks of dirt, traces of minerals, all moving backward through channels and pipes that once worked tirelessly to perfect them. This entire reversed sequence reveals an important truth. The clarity of glass depends on the purity of its ingredients. Without this stage, skyscraper windows wouldn't shine. Solar panels wouldn't capture sunlight efficiently. Medical glass wouldn't meet safety standards. Everything begins with the cleansing of something ordinary into something exceptional. But now, with purity fully undone, our backward path leads to the beginning of the entire chain, the raw extraction of sand from the earth. It's time to return to the mines, where the journey of glass truly starts. As we rewind past purification, the sand leaves the controlled environment of the factory and returns to the vast outdoors. Conveyor belts pull the material backward across long steel frames, carrying it out of the plant and onto enormous transport trucks. Tires roll in reverse, backing away from the loading bay. Each truck grows lighter as the sand rises into the air and pours backward through its open bed. Soon, the entire mountain of material lifts from the fleet and floats back toward the landscape where it was originally mined. In forward time, industrial excavators carve deep into ancient deposits, riverbeds, open pits, and coastal dunes rich in silica. But now, moving backward, the ground slowly refills. Steep cuts rise like time-lapse healing wounds. Bucket loads rejoin the earth grain by grain, rebuilding the terrain as if untouched by human hands. Excavator arms swing in reverse, returning sand to the soil with smooth, sweeping motions. The metal claws unclench, releasing material back into the earth instead of tearing it free. The scene reveals the sheer scale of extraction required to fuel modern manufacturing. One glass plant can process thousands of tons of sand each day. Yet in reverse, that enormous flow seems to vanish effortlessly into the land. Haul trucks drive backward along dusty roads, heading away from the mine instead of toward it. Their heavy engines hum in reverse as they return to a resting state. Even the wheel marks left in the dirt fade away as drifting grains sweep back into place. Watching the mining process unwind shows how much work is needed before sand ever reaches a furnace. Geological forces shaped these silica-rich deposits over millions of years. Wind, water, and pressure refined them long before machines ever touched the ground. And now, as we peel back those final layers in reverse, the sand settles into a calm, untouched landscape, one that looks almost as ancient as time itself. With the mines restored, our journey is nearly complete. We've reversed the story of glass through every stage, melting, shaping, testing, purifying, and mining. There's only one final step left, returning to the smallest, simplest beginning of all,